So far, whenever we've had a letter, we've used it to represent a single numerical value, something like, say, x equals 2, y equals 4, z equals 7, something like that. And it didn't matter what number it was. We could have had something like, say, 2.5 instead of just 2. We could have had 7/10 rather than just 7. It doesn't really matter, but we've used our letters to stand for, to code for a particular single numerical value. Thing is, sometimes in problems or in life, we might not know the exact value of the letter. We might just know what the letter is in relation to something else. We might know, for example, that x is some number that's bigger than 3. We don't know exactly what, but we know that whatever it is bigger than 3. We might know that x is less than 9. Whatever it is, it's something that's less than 9. We might know that this letter, again, x, is between two values. We might know that it's somewhere between -3 and 2 because of some context information in the question. We just might not be able to be more exact than that. Now the problem is, these, as they are, these equalities with their equals signs in, these are very exact. X is 2.5, y is 4, and z is 7/10. They are indisputable facts. They are definitely true. The two things are exactly the same. But really, we need to be able to have a way of describing, using symbols, this idea of comparison, this idea of bigger than or less than or between. So we introduce a couple of extra symbols where that means exactly the same, and then we introduce these two symbols. And these two symbols are used to describe less than and greater than. Which is which? Well, it depends which way round you're using them. It depends which way round you're reading them. There is a way of recognizing which way round you're reading it, and we'll come to that in a moment. But either could be used to describe either relationship. Depends which way around you're reading it, depends which way around you're using them. We also need to have a couple of extra symbols because these symbols here suggest less than, as in strictly less than 3. Anything at all that is less than 3. So not 3 or bigger. Greater than. Strictly greater than. Greater than 4, for example, means bigger than 4, as in not 4. We also need to have two very similar symbols where we can include those endpoints. So we have these two with a little line underneath. It's a little bit like we've combined these two with the equals. We've got the little line underneath, and these are for less than or equal to and greater than or equal to. These include those endpoints. So we're talking about, say, something being less than or equal to 4 means strictly less than 4, or in fact 4 itself. Greater than or equal to 10, strictly bigger than 10, or in fact 10 itself. These endpoints not included, just less than, just greater than, these endpoints are included, and we have the slightly different symbols for each. Now there is often a lot of confusion around which way round the symbols are. And as I said before, either could be used to describe less than, either could be used to describe greater than. It depends which way round we're reading them. So there are two ways you can remember it. We can think of them being a little bit like an arrowhead. The idea being that it points to the smaller value. So whether we're setting up two numbers or whether we're setting up a letter and a number, the larger one goes here on the open end, the smaller one goes here on the pointy end because it points to the smaller value. There's our first way of looking at it. The second way of looking at it, admittedly it's a little primary school perhaps, but it doesn't matter, it works. The crocodile would rather have a bigger meal than a smaller meal, so the crocodile will put its open mouth around the larger value. So either the symbol will point towards the smaller value, or the crocodile will eat the larger amount, i.e. the bigger value will go at the open end of the symbol. For example, if I wrote this, we would generally read these things from left to right, same as we would any bit of maths. You can read it the other way, but we're usually going to read them left to right, and we're usually going to put the letter on the left where possible. There is some letter, X, that stands for a particular number. We don't know anything about that particular number other than it has this relationship to 6. Well, the arrow points to the smaller value, or the larger side is the one at the open mouth. So the X pointing towards the 6 is the smaller value, which means whatever X is bigger than 6. Can X be 6? X cannot be 6. We do not have the little line underneath. X has to be strictly bigger than 6. So if we're just thinking whole numbers, it could be 7, 8, 9, 10, 11, and so on. If we're including decimals, anything that's a little bit bigger than 6, but not 6 itself. So 6.0000000000000000001, for example, would be bigger than 6. That would be okay, but 6 itself would not. Next one. The arrow points towards the smaller value. So here y is the smaller value and 10 is the bigger one. It's on the open end. So in this case, whatever y is smaller than 10. But again, we don't have the little line underneath. We are not including the 10 as an endpoint. So y is strictly smaller than 10. P is on the open end of the inequality sign. P is on the open end of this sign. P is the larger one. So P is greater than -3. But this time we have to notice that there is that little line underneath. So or equal to -3. So bigger than -3 or -3 itself. We're including the endpoint this time. And finally, W is on the smaller side. The arrow points to the smaller side. The arrow points to the smaller value. The 3 is on the open mouth side of the crocodile. It is the larger value. So W is smaller than 3 or 3 itself. Notice that I've phrased this in two different ways. Either of those are perfectly valid. You can either say greater than or equal to, or less than or equal to, or you can say smaller than the value or the value itself, greater than the value or the value itself. This is an equals. These four are all what are said to describe inequalities, which kind of makes sense. If two things are not equal, they are unequal inequalities. This idea of describing a relationship, a comparison, without describing something as being equal to something else. There's one final setup of inequalities that we might need to be aware of, and that's when we are looking at something like this. What seems to be a double inequality, this idea of two symbols. What we can do is we can look at this as two separate things. We could look first of all at this. Here we have a 2, we have an x, and a comparison being made. The x is on the open mouth side, the 2 is on the pointy side. So the 2 is smaller than the x, which means x is bigger than 2. Now if we look at the other half of the inequality, if we look at the second half, if we look at this bit here, and look at the x and the 6, comparison is being made between the two. The 6 is on the larger side, the x is on the smaller side, the x is being pointed towards, and the inequality sign always points towards the smaller value. X must be then smaller than 6. Now if x is bigger than 2, whatever number x stands for is bigger than 2, and if whatever number x stands for is smaller than 6, we could just combine those two things together and say that x is between 2 and 6. Bigger than 2, smaller than 6, it must be between the two values. Can we include the 2? Well, no, we can't, because the x is strictly bigger than 2. Can we include the 6? Well, no, we can't, because the 6 is strictly bigger than x. The x is strictly smaller than the 6. We can't include the endpoints here. Sometimes we might be able to. You could get these setups. Any setup like this describes a between relationship. These two symbols could be either. They could be including the endpoints, they could be not including the endpoints. Something to notice though, they will always point in the same direction. They will have to, because they will have to point down towards the small one. If I were to cover up the middle bit, say, this bit here, that is still a true relationship. 6 is still bigger than 2. So everything holds up. Here, x is between 3 and 9. Including 3 and 9. So if we're just looking at whole numbers, x could be 3, or 4, or 5, or 6, or 7, or 8, or 9. Y is between 11 and 15. This time the 11 is included. The 15 is not strictly smaller than the 15, but the 11 is included, so we can have including 11. Write down the possible whole number values of x. Something like that, for example. So x is between -4 and 1. We can include the -4, we cannot include the 1, and we are only thinking whole number values. So -4 is included, -3, -2, -1, and 0. We can't include the 1, they are the only possible values that x could take if we are sticking with whole numbers. One tiny change to this question that might be made, rather than use the words whole numbers, we might see a different word. We might see the word integer used, which is just a fancy word meaning exactly the same thing. Integers, whole numbers. We may have to draw this inequality on a number line. So here is a segment of a number line. Notice that I'm just showing a small segment of a number line. I need to somehow describe on this number line all of the values of x that are bigger than 6. Is the 6 included? No, because we don't have that line underneath. So I'm going to mark my endpoint. I'm always going to start with the endpoint. And if the endpoint is not included, then I'm going to draw an open circle at that endpoint to show that it's not included. I'm only interested in all the values of x that are bigger than 6. The arrow points towards the smaller value, it's pointing towards the 6, therefore the 6 is the smaller of the two, so the x is bigger. I'm interested in every value of x that is bigger than 6, so I'm going to draw an arrow above my number line, extending past the 6. And I've shown on my number line that x is bigger than 6. Something like this, for example. I have another snippet of number line. This time, my endpoint is included. So my endpoint is the 3. I'm going to draw a circle at 3 to show the endpoint, but because it is included this time, because we're looking at this less than or equal to, I'm going to colour in the circle. I want all the values of w that are less than 3. The arrow is pointing towards the w, therefore the w is the smaller value, so the w has to be less than 3. So I'm going to have my arrow point down to show that I'm looking for everything less than 3. One final one on a number line. We might have to represent on a number line one of those between inequalities. Something like that, say. So I'm going to have my snippet of number line again. There we go. 2 endpoints this time, looking at the 3 and I'm looking at the 9. So we're going to have a circle at the 3 and a circle at the 9. What kind of circles? Well, it depends whether the endpoint is included. If we're not including the endpoint, we're drawing an open circle. If we are including the endpoint, we're drawing a closed circle. The 3 is not included, so we're going to draw an open circle at the 3. The 9 is included, so we're going to draw a closed circle at the 9. I need to somehow have an arrow that comes up from the 3 and down from the 9. In fact, the x is quite happily sandwiched between those two values. So all I need to do is draw a nice straight line between the two. Now x is represented by everything underneath that line that's strictly bigger than 3 and strictly less than 9. Just to really hammer that point home about the circles as well. If we have got an open circle not included and a closed circle included. It is also possible that you could be given a picture of a number line and asked to switch back to the written inequality form, but it is exactly the same question, just the other way round. We'll just have a look at the one example. I'm going to solve 3x minus 4 is less than 17. So the 17 is bigger. The 17 is on the open side. The equation is on the smaller side. This says there is some value of x that when we times it by 3 and then take away 4, we get a value that's less than 17. In fact, there are lots of values of x. Just to pick one out of thin air, 0. 3 times 0 is 0. Take away the 4 is minus 4. That is less than 17. But there are lots of values that won't work. Pick one out of thin air, 10. 3 times 10 is 30. Take away the 4 is 26, which is not less than 17. So 0 works, 10 doesn't. There is some end point then where we switch from ones that work to ones that don't work. And we need to work out what that is. What is that pivot value? X is more than a certain value or less than a certain value or whatever. We're always going to deal with these in the same way if we're solving equations to do with inequalities. We are going to first of all ignore this sign and say, what if it wasn't equals? So step 1 is going to be, we're actually going to solve that. We're going to swap the inequality out and swap an equals in, and we're going to solve that. because we know how to solve that. That's something that we can do. And presumably, this and this are linked in some way. They are going to be similar. So to solve this, we start with our x. First thing we do is we times it by the 3. We take off the 4, and that spits out 17. This is a classic function machine kind of problem. So I'm going to put the 17 back in. I'm going to add 4 this time. And we're going to divide by 3. 17 plus 4 takes us to 21. And dividing by 3 gives us 7, which means when we solve the equality, x is equal to 7. And step 2, then, we're going to notice that we didn't have this originally, we had this. What happened to get from here to here? We swapped out the inequality sign and swapped in an equals. All we're going to do at the end is we're going to swap it back. We're going to swap the signs back. So, our final answer then will be that x is less than 7. So we are saying that any value of x that is less than 7, strictly less than 7, will give us a final answer. When we do this to it, times it by 3 and take off 4, will give us an answer that is less than 17. We could even test that out if we wanted. We could pick a value that's less and check that it works, pick a value that's more and check that it doesn't. If we pick a value that's less, what's less than 7? 6. Okay. 3 times 6 is 18. Take away the 4 is 14. That's less than 17. So that works. We know what 7 does. We know that 7 spits out exactly 17 because that's where this came from. So let's check one that's more and check that it doesn't work. Let's pick 8. 3 times 8 is 24. Take off the 4 is 20, which is not less than 17, but that's good because we weren't expecting it to be. We were expecting the 8 to not work. So there is our final answer. X is less than 7. It's worth noting when we are solving to do with inequalities, solve it like we would for the normal equation. So we're going to swap out the sign, whatever it is. We're going to put an equals in. We're going to solve it like we normally would. Function machine or scales usually. And then we're going to swap the sign back in at the end. Notice also that it's the same sign that we've swapped back in. Otherwise, we are changing the original inequality. So when we swap the signs back, it has to be the same sign that we got rid of originally.